Hello and welcome to my CHEM561 Advanced Organic Synthesis Final Molecule Project. My name is Robert Williams, and in this presentation, I'm going to show you a target molecule and then try and synthesize it using available reagents, and then work with those and reactions we have learned in the class to produce that final molecule. So to start this off, I just want to look at the chosen molecule. Of the options given, I chose the first molecule present. As you can see on the left, we have an aromatic ring. That then leads into a cis alkene. Going down the molecule further, we see we have two alcohols in anti-fashion in the 1,3 positions. And then going at the end of the molecule, you can see that there is a six-membered closed lactone present. I'm pointing these out because these features in the molecule help to kind of identify where we can bond and react and synthesize the molecule. And I'll be using them during the synthesis to create this final product. A good place to start when trying to synthesize a molecule is working backward and doing retrosynthetic steps to kind of see where a good base to start would be. Looking at the current molecule, you can see that I'm splitting it in between the alcohols. And by splitting that and then working a little bit backwards, we would get a ketone and an aldehyde, which can be combined via enolate reaction to create this final product once everything is reduced to the alcohol. So now that we've split the target molecule in these two separate pieces, let's take a look at how we can start from that A and move backwards to maybe a more approachable starting molecule. As you can see from this chunk, we have an aromatic ring, we have a cis alkene, and we have a ketone. Now, working backwards, creating a ketone is not difficult. All we need to really do is have some sort of leaving group and use maybe a Grignard reaction. And then to create that alkene, why don't we start with something like an alkyne? An alkyne will allow us to both attach that other group that you see there, more of the carbonyl, as well as reduce to a cis alkene. And then once we have that alkyne, we can split it off again into these two pieces. With this aromatic ring plus alkyne actually being a molecule phenylacetylene, and the group on the right we can work to synthesize. So using retrosynthesis, we were kind of able to see areas and functional groups, how they can react, and work backwards to a good starting point for our synthesis. So let's do the same thing for the second molecule that we use to synthesize the product B. As you can see, we have an aldehyde and we have a lactone in this chunk. Working backwards, I know that to open or to create a lactone, we need an alcohol and we need a carbonyl with some sort of leaving group. In order to form that, we're going to have to get rid of that other aldehyde. So working backwards, we can convert that to an alcohol and then an alkene, which won't interfere. And then by opening up the ring, we can see that if we have an alcohol and then a carbonyl with some leaving group, if we can create that, we can then create that lactone. So to create that, we can use something like a Grignard reaction, in which we create that alcohol from addition with a carbonyl. And then the Grignard, we can go back, and there's actually a molecule, ethyl 4-bromobutanoate, which can be used as a starting material. It is the exact same as that final molecule, except that there is an ethoxide group where that leaving group is. And so starting with that, we can work backward to try and create that final product you see. Now that the retrosynthesis has given us an idea of the different stages of the molecule, let's work with our starting materials to try and move forward and synthesize this molecule best we can. Starting with phenylacetylene, if we react this with NaNH2, it'll deprotonate the alkyne, and then that deprotonated alkyne will react with ethyl 3-chloropropanoate at the carbon attached to the chlorine, using chlorine as a leaving group and then leaving us with this product here, which has the aromatic ring, the alkyne, and now it has the carbonyl in the form of the ester group. So the next step that I have in this synthesis would be to use hydrogen as well as Lindlar's catalyst to reduce that alkyne to an alkene, making sure to maintain that cis stereochemistry. It is important to use Lindlar's catalyst and hydrogen as opposed to other reagents such as lithium or sodium, as these can actually lead to a trans alkene, which is not exactly what we want in this targeted molecule. So again, using this catalyst that we have here allows us to keep the stereochemistry that we would like. So the last step in our synthesis to create that first target molecule A is to perform a Grignard reaction. This can be done using bromomethane, reacting that with magnesium to create the Grignard reagent, as you can see in that second reaction. And once you introduce this, as well as water, into our reaction, the methyl group will replace the ethoxide to create that final product you see there. This now is our first target molecule. We can now work to try and synthesize the second one, named B, in order to get those two targets that can be used and reacted together to create our final product. Now to try and create that lactone and aldehyde molecule B that we saw earlier, we will start with ethyl 4-bromobutanoate and react that with magnesium to create a Grignard reagent, which will be used in the following step. So the Grignard reagent synthesized in the previous step can now be used to react with prop-2-enol to create the product on the right. There are certain considerations that need to go into this reaction, however. As you can see that there are two different carbonyl groups that can react with the Grignard reagent. You have the ester attached to the molecule, and you have the aldehyde attached to the prop-2-enol. Now, it is important to note that that aldehyde is going to be more reactive, and so it'll have preference for the Grignard reagent. However, in order to prevent any kind of side products, we're going to be using 0.9 equivalents so that there is not enough to react with the ester. So in this next step, we are going to start our creation of the lactone. To do this, we are going to use potassium terbutoxide to deprotonate the hydrogen coming off of that alcohol. It is important to use a larger base for this, as it has less accessibility toward the alpha carbons or alpha hydrogens coming off of the ester group, which other reactions it could react with to create an enolate. However, due to the size of the base, it'll actually more preferentially deprotonate that alcohol. So once that alcohol is deprotonated, the oxygen there, you can see that I do a bit of a structure shift where I move the ester group closer to the ethoxide, and that is because it will react at that carbon of the carbonyl to create the lactone in the following step. Carrying over from the previous step, you can see how that oxide group is going to react with the carbon of the carbonyl of the ester. It is going to shift the electrons up to the oxygen, and then those electrons are going to come back down and kick off the ethoxide group. This will give us our final lactone product with the alkene still in place. With the lactone now formed, we can work on the other side of this molecule to try and create the aldehyde that we will need for reactions later in the synthesis. To create the aldehyde, the first step of this will be to oxidize that alkene to an alcohol. If we want to do this at the less substituted position, using a reagent such as the BH3, the borohydride, is helpful as it preferentially oxidizes the less substituted carbon, as you see here. This alcohol can now be oxidized using PCC to create the aldehyde product that you see here. This product is the molecule B, which we will need in the following reactions in order to create our final product. So after this oxidation, we finally have our second building block to move forward in the synthesis. Now that we have those two target molecules A and B synthesized, we can react those two together to work towards our final product. Now, it is important to remember that there is a stereochemical element to this synthesis. In order to maintain the stereochemistry that we want of the diols, we need to first react this structure here, this ketone, with the camphylborane complex in order to promote the proper stereochemistry. So by reacting with this camphylborane complex, what this is going to do is it is going to prevent the orientation of this enolate being in front of the aldehyde molecule, the other molecule we synthesized. Because this complex, this camphylborane complex, is going to block the back of this molecule, it's only going to be able to form an enolate reaction going forward, which will push the oxygen of the carbonyl, the aldehyde, out. To try and visualize this better, I've tried to adjust these molecules here so that this aldehyde is coming out of the page, and this borane complex, the way the enolate is more behind it. Because of the borane complex, we're not going to be able to have any reaction where the aldehyde is behind the phenolate right now. And so it is only going to be able to attack the aldehyde from behind. That's going to push the oxygen of the aldehyde forward, giving us the stereochemistry you see in the intermediate, where the alcohol is coming at us. And then to remove the borane complex, we're going to use ethanol amine, and then that will give us the product you see over here on the right, which is almost done to our final target. And finally, the last step of this synthesis is going to be a reduction of that ketone. However, it is important to note that we need to maintain the stereochemistry that we want, which is anti to that other alcohol present. And to do this, we are going to use an acetylborohydride compound. This is going to create a complex that you can kind of see in this transition state down here. I apologize, it is a little bit convoluted, but what this does is that it prevents attack from the back position. It kind of blocks off that area and promotes a hydride addition from the front, which will then push the alcohol or the ketone / alcohol to the back, creating that anti-stereochemistry. And after that final reduction, we have come to our target molecule. Starting from the phenylacetylene and the chloropropanoate reagents we initially had, we were able to react those using reactions learned throughout the course to both maintain stereochemistry, create the proper functional groups, and overall finalize this molecule. It is important to note that this is just a proposal on how we can synthesize this molecule. There are various other methods and pathways to do so, and there are other considerations that certainly need to go into this to perform it in a practical lab setting. I'd like to thank you for watching my presentation. I hope that it was informative on just how we go about molecular synthesis in terms of the retrosynthesis and then forward, and in terms of the chemistry, the different reagents and reactions we can use, and how we can maintain the stereochemistry. Below here, you just see a list of the chemicals that I used that are real and can be purchased. And other than that, I just want to say thank you, and I hope that you learned something from this presentation.